Okay, I just took this setup from the previous video we did about the beta function and proving that. So this is just, we're going to prove the Legendre duplication formula today. And it's actually pretty simple. Actually, no, it's not. It's kind of crazy looking, actually. If you take gamma of a number, and then gamma of z plus, of that number plus 1/2, then there's actually a way to express this in terms of the gamma function, but with a nicer input, and that's going to be 2 to the 1 minus 2z square root of pi, and then gamma of 2z, if I'm not wrong. Okay, so that is the Legendre duplication formula. How the hell are we going to prove this? We're going to be using the beta function. Okay, and we're going to start by plugging in, okay, sorry, not into here, but into here. We're going to take a look at this expression right here. Now, what are we going to do here? We're just going to plug in the same number for both x and y. Seems pretty interesting. So if we take beta and just plug in the same value, say alpha, okay, if we plug in beta of alpha comma alpha, well, on the right hand side, that's going to give us gamma of alpha times gamma of alpha, which is just gamma squared of alpha, and I'm pretty sure this is valid notation, okay, over gamma of 2 alpha. All right, where we're going to go from here, we're going to write this in terms of the integral definition of the beta function. Okay, but just remember this, okay? Now, plugging this into the integral definition of the beta function, we're going to integrate from 0 to 1. We're going to have t to the alpha minus 1, and then 1 minus t to the alpha minus 1, and then dt. Okay, now we're going to make a very specific substitution that's going to allow us to leverage some symmetry. But before we do that, let's go ahead and consolidate this down a little bit more. We're going to have the integral from 0 to 1. And basically, see these powers are the same. I'm going to drag the two bases together. So that's going to be t times 1 minus t. Alpha minus 1 dt. Okay, so what's the substitution we're going to make? Let me check my notes. It's going to be t equal to u plus 1 over 2. So let t equal to u plus 1 over 2. And there is some reasoning behind this. First of all is the bounds, okay? Let's go ahead and just isolate u for a second to see how the bounds are going to turn out. Multiply 2 on both sides, so we're going to get 2t. And after that, subtract 1, so 2t minus 1. And this is going to be equal to u. Now, one reason why we're going to make the substitution is because the bounds are pretty nice. It's going to make it symmetrical. Because when t is equal to 0, okay, that's the lower bound, 2 times 0 minus 1 is just u. And that's just negative 1. And when you plug in t equals 1, right here, 2 times 1 is 2, 2 minus 1 is 1. So the upper bound in the u world is going to be 1. So this is going to be symmetrical. That means if that inside happens to be even or something like of the sort, then we're going to be able to leverage the parity like property of the integral function, right? Inside here, we're going to just go ahead and plug in u plus 1 over 2 for this first factor. However, for the second factor, we're able to simplify this down a little bit. So 1 minus u plus 1 over 2, okay? How are we going to simplify that? 1 minus t is just u plus 1 over 2. Okay, 1 is just 2 over 2. Okay, so if we combine the two, then we're going to get 2 minus u plus 1. And if we go ahead and distribute the negative sign, then we get 2 minus u minus 1 over 2. And this 2 minus 1 just gives you a 1, so this ends up being 1 minus u over 2. So this other factor right here, 1 minus t, is just 1 minus u over 2. So I'm going to rewrite this. We're going to get 1 minus u over 2. And then this is going to be raised all to the alpha minus 1. dt is, if we go ahead and differentiate this, we'll see that dt is just, this is just u over 2. When you take the differential of that, you're going to get du over 2. And then the other side is just 1/2, but when you take the differential, it's going to go to 0 because it's a constant. So dt is just du over 2. I'm going to write this on the outside right here. So the over 2 is on the outside, and the du is right there. Okay, that's nice. Why? Because the inside is just a difference of squares now. We can go ahead and rewrite it. And once we do, we'll see that there are some nice properties of the integral that we can leverage. The 2's are going to multiply. So 2 times 2 is 4. I'm going to write down 4 first. And then just simply distribute the alpha minus 1 onto the power of the 4. Okay, next we have the numerators. 1 plus u times 1 minus u is just 1 minus u squared. So we're going to have 1 minus u squared to the alpha minus 1. Okay, du closes it off. First of all, this denominator right here is independent of u, okay? So that means we can treat it like a constant and move it outside the integral. But that's not the important part right now. In fact, what's important is the inside is actually even. Why is it even? Well, because if you plug in u and you plug in negative u to just this function right here, okay, the integrand, you're going to get the same thing. Because u squared is the same thing as negative u squared. They're both just u squared. So that means this integrand is even. Now, when you have an even integrand, that just means it's symmetrical on both sides. Okay, so for example, that's an even function. And now we're integrating from over symmetrical bounds too. So -1 to 1, all right? Well, this is, we can integrate over the whole thing, or because this area on the right-hand side is the same as this area on the left-hand side, we can just integrate over this guy only, right? And then just double it to get what we originally had. What's that going to look like? Well, I'm going to leave room to move this outside in a second. That's going to look like, we're going to start at 0 and go to 1 instead. Okay, the inside's still going to stay the same, because the function, of course, has to stay the same. 1 minus u squared to the alpha minus 1 du. But then we're going to have to multiply by 2, right? Because we're integrating over just one copy of this. But there's another one that we had to account for. So there must be 2 of these guys to account for this entire area here. Okay, next I want to move this. Well, actually, so this 1/2 and this 2 that just appeared out of this integral are going to cancel out. So the only thing that we're going to be we're going to need to deal with is just 4 to the alpha minus 1. Now, that's going to be in the denominator. Let's do a scratch workout here. 4 to the alpha minus 1, but that's going to be in the denominator, because right here it's in the denominator. First of all, if we add a negative sign in the exponent, we take its reciprocal. So that's just going to flip this guy to the top, but it's going to make the exponent negative. And that translates to reversing the order of subtraction. So instead of a alpha minus 1, you get 1 minus alpha. And see here how inside of this is base 2. We're going to do that with this too. So 4 we can rewrite as 2 to the power of 2. Okay, and then this 2 is going to multiply to the original power of 1 minus alpha. We're going to go ahead and just distribute that in. So we get 2 minus 2 alpha. So right here, this constant of 1 over 4 to the alpha minus 1 is going to become 2 to the 2 minus 2 alpha. Okay, hopefully that wasn't too confusing. Okay, this is all the work that we just did to get this new coefficient. All right, so that is one representation of this integral, but there is another way to get there. Okay, but that other way to get to this right here, which I just copied down from down there, we're not going to plug in numbers directly into the beta function anymore. Instead, what we're going to do is we're going to take the beta function and observe a couple of its properties. Okay, we're going to do an integral. We're just going to take the integral definition then, I guess. So t to the x minus 1 times 1 minus t to the y minus 1 dt. Now, right here, this kind of matches up. You see how this second factor looks sort of like the inside of this? If you just let t equals, say, let's use a new variable, s squared, wouldn't that look the same? Well, we can try it. Let t equal to s squared. Then now dt is going to be 2s ds. And yeah, okay, so the bounds, well, let's just go ahead and copy this down. The bounds, when t is equal to 0, for s squared to be 0, s should also be 0. Because 0 squared is just this 0 right here. Same deal with 1. If you just plug in s equals 1, 1 squared is just 1. So the upper bound should also go to 1. Inside of here, t to the x minus 1, well, t we just set to be equal to x squared, s squared. This squared is going to distribute into this power right here. So we're going to have 2x minus 2. 1 minus s squared, okay, because t is s squared. And then y minus 1 is just going to stay as the power. And the differential element, dt, is just 2s ds. I'm going to move the 2 to the outside. Hopefully that's okay. And then, yeah, so that's fine. S, we can multiply that into here. Let's write down the ds first. So we're going to take care of the s now. When you multiply s in, you can combine it with this power right here. And, well, that's just going to increase the power by 1. So we're going to go from negative 2 to negative 1. So now let's try to find inputs that we can plug in into this definition of the beta function to make this look more like that. Now, notice that this second factor right here is already kind of taken care of, because all you need to do is for the y input of beta, all you need to do is plug in an alpha. After you plug in an alpha, this right here is going to exactly match that right there. So the second input, the y input, is going to be an alpha. Right here, this factor doesn't exist in our other, integral. So what we're going to try to do is make it equal to 1. And how do we make this guy equal to 1? Well, recall that any number that isn't 0 raised to the 0th power returns 1. So basically, you have to find a way to make this exponent right here equal to 0. If you plug in x equals to 1/2, you're going to get 2 times 1/2 minus 1. 2 times 1/2 is just 1. So when you plug in x equals 1/2, this whole thing becomes 1 minus 1, which is 0. And that works, because when you have s to the 0th power, that's just 1. So for x, let's plug in 1/2. Okay, so x is equal to 1/2. So what's that going to get us? Well, this 2 is going to stay on the outside. We're going to have the integral from 0 to 1. Remember that the exponent goes to 0, so this whole factor goes to 1. So we're going to just ignore it. And then the second factor, 1 minus s squared, the y we set to be alpha. So we're going to have alpha minus 1 ds. And, well, this right here is now exactly in the form of that right there. Let's go ahead and just make one change, and that is to isolate this integral. So right here, I'm just going to divide by 2. We're going to get 1/2 times beta of 1/2 comma alpha. And this is just going to be equal to, I'm going to be lazy and take that and put it right there. All right. All right, so very simply what I did was, well, we saw that that integral can also be expressed as 1/2 of beta of 1/2 comma alpha. So this integral now, well, we can rewrite it as that. So here's what we're going to work with. We're going to get rid of all this work from here. And we're going to deal with just these two right here. So we have this gamma thing, and we have this whole thing right here. Let's copy this down one more time. So this implies that gamma squared of alpha over gamma of 2 alpha. On the right hand side, we'll have this 2 to the 2 minus 2 alpha. 1/2. Okay, 1/2 from this beta right here. This is just 2 to the negative 1. Okay, and when you have 2 to the negative 1, you can combine the powers of both of these because the base is both 2. When you combine the powers, this 2 is going to drop to a 1 because 2 minus 1 is obviously 1. So yeah, that we took care of that 1/2. Now we just have beta of 1/2 comma alpha. This we can once again rewrite using the gamma function because we have this equivalence right here. So beta of 1/2 alpha is just gamma of, and I'm only referring to this part now, all right, not the 1/2, we took care of that. Gamma of the first input, so 1/2, times gamma of the second input, which is alpha, over gamma of 1/2, which is the first input, plus alpha, which is the second input. So let's go ahead and copy this down right here. But with one thing, gamma of 1/2, if you plug it into the integral definition, you'll find that it is equal to the Gaussian integral over the real number line. And you can do some manipulation to find that. All right, I'll leave that up to you guys, but you'll eventually find that this is equal to square root of pi, which is the Gaussian integral. Okay, but besides that, everything else we're going to just keep the same. So gamma of alpha over gamma of 1/2 plus alpha. Okay. So right here, we can do a couple of things. This square, we can go ahead and straight up cancel with this whole gamma of alpha. And then let's just multiply this on that side and then this to that side. So finally, we are almost done. Gamma of alpha, we're going to keep this like remaining gamma, okay? Then after cross multiplying by this guy right here, you get gamma of 1/2 plus alpha equals 2 to the whatever, 2 to the 1 minus 2 alpha. Then we have square root of pi. Okay, that's from here. And then we're going to cross multiply this, and you're going to get gamma of 2 alpha. And that's it. Okay, we see that we literally just derived exactly what I had written up here for the Legendre duplication formula. So we have found this new equivalence and property of the gamma function.